Today, we're discussing applied optimization, sometimes simply called optimization, sometimes called constrained optimization. We're going to be finding in these problems a maximum or a minimum. So the math is very familiar. You've done it before. Derivatives, critical numbers. But the difference here is you're not going to be given a function. You will have to come up with the function. And all of these problems will have certain elements in common. Somewhere in the wording of the problem, you will find an objective function. That is an equation for the quantity that you're trying to optimize. In addition, you will find a constraint. As I said, these are sometimes called constrained optimization problems. A constraint is a limiting factor, something that must be considered when coming up with your objective function. So let's take a look at some of the problems that we'll have to do, or problem types that we'll have to encounter here. First problem. We are being asked to design a rectangular steel tank with a square base and an open top. So it is always a good idea to start by drawing a diagram of what you're dealing with. A rectangular steel tank with a square base and an open top. That is, no top. Since it's a square base, we will label the base x by x. The height makes sense to label h. As I said, the tank is to have a volume of 500 cubic feet. Therefore, we'll set our volume equation, length times width times height, that is x squared times h, equal to 500. This is our constraint. We're not solving for the volume. We're not trying to optimize it. That's fixed. We want to use this constraint, and you'll see exactly how momentarily. Given this volume, our task is to find the dimensions that will minimize the amount of material. The amount of material is equivalent to the total surface area of the tank. There are 5 surfaces here, a bottom and 4 sides. The area of the bottom is x squared. The area of each side is x times h, and there are 4 of them. That is the amount of material, the total surface area. As I said, this being the equation giving us the quantity that we're trying to optimize, in this case minimize, this is the objective function. This constraint enables us to do something that is absolutely essential. That is to rewrite the objective function in terms of just one variable. We will take this h and set it equal to 500 over x squared. Now we can substitute in this expression for the h. So the total surface area is x squared plus 4x times 500 over x squared. Simplifying that yields x squared plus, well, this x will cancel with one of those x's, yielding 2,000 over x. Now we have our objective function in terms of simply one independent variable, x. At this point, the problem becomes very familiar. It's a problem that we've done before. That is, taking a derivative setting the derivative equal to 0 to find the critical number. So let's do that. dA dx equals 2x. Right, no, 2,000 over x is 2,000 times x to the negative 1. The derivative of that is negative 2,000 x to the negative 2, or minus 2,000 over x squared. And we set that equal to 0. Okay. If a minus b equals 0, then of course a equals b. Multiplying through by x squared yields x cubed here. Dividing by 2 is 1,000. So moving over, we have x cubed equals 1,000. So x equals 10. Now the question you might ask at this point is, how do I know that that 10 yields a minimum surface area as opposed to a maximum surface area? Well, we can test that very easily. The smallest possible value for x is 0. There is no given largest possible value, but if we just look at the derivative from 0, and our only critical number is 10. If we test the intervals here, take a look at what happens. Suppose x is less than 10, like 5. Well, the derivative, if x is 5, would be 10 minus 2,000 over 25. 2,000 over 25, I believe, is 80. In any case, that would be negative. That is, the surface area would be decreasing from 0 to 10. If x is greater than 10, like 20, your derivative would equal 40 minus 2,000 divided by 400, 20 squared. 40 minus 5 is definitely positive. So, clearly, when x equals 10, the surface area attains a minimum. And there is no other critical number. This is not going to come back down again. Therefore, we know that it's a minimum. If x equals 10, h equals 500 divided by x squared. 500 divided by 100 is 5. Those are the dimensions that would minimize our surface area, the amount of material. And that's the way we do problems like this. In general, you're going to have an objective function and a constraint. The objective function will usually have more than one independent variable. We want to reduce that to 1. That is the value of the constraint. Let's take a look at another problem that is not quite so real world in its composition, but it's a common type of problem here, and that is an inscribing problem. The elements will be the same. We are being asked in this problem to find the rectangle of greatest area that can be inscribed in a semicircle of radius 5. In order to do a problem like this, let's put our rectangle and semicircle on the coordinate plane. Semicircle of radius 5. That is the top half of a circle of radius 5. In that semicircle, we are going to inscribe, a rectangle. Its base will be on the x-axis. Its vertices, its bottom vertices, will be at x and negative x. Top vertices on the circle. Now, there are an infinite number of rectangles that can be drawn in this way. Some wider than others, some narrower, some taller, some shorter. Only one of them will have a maximum area. How do we find that rectangle? Well, first of all, we have to find a formula for the area of a rectangle. Let's start with the basics. The area of a rectangle is the base times the height. The base is easy to express in terms of x. If it runs from negative x to positive x, the base is 2x. The height is clearly the y coordinate here. Remember what this arc is. It is the top half of the circle with, in this case, its center at the origin and a radius of 5. Going back to our pre-calculus work, we should remember that any circle with its center at the origin has equation x squared plus y squared equals r squared. Since our r is 5, the equation of this circle is x squared plus y squared equals 25. If we solve for y, we will now have the height of the rectangle in terms of x. Y squared equals 25 minus x squared. Y equals, now, since we are looking only for the top half of this circle, our y is the positive square root of 25 minus x squared. A warning at this point. Do not dare to say that that equals 5 minus x. There are very few crimes in mathematics that I consider capital offenses. That would be one of them. All right, y is simply the square root of 25 minus x squared. That is the height of our rectangle. So here is our formula for the area of the rectangle in terms of just one independent variable. In the previous problem, we were able to express one of the variables in terms of the other. In this problem, we expressed both of these in terms of the third, which was x. At this point, again, the mathematics is familiar. It should be, at this point, very common, almost automatic. Find the derivative, set the derivative equal to 0, and solve for your critical number. Now, here we know what the domain of x is. The smallest possible value of x is 0, the largest possible value is 5. We have a closed interval, but we'll deal with that in a few minutes. dA dx equals, we have a product rule with, of course, a chain rule. 2 times the square root of 25 minus x squared plus 2x times 1 over 2 times the square root of 25 minus x squared times negative 2x. Well, let's do some simplification here. We can cancel there. So this equals 2 times the square root of 25 minus x squared minus 2x times x, 2x squared over the square root of 25 minus x squared 0. Again, as we often see, we've got an a minus b equals 0, which means that a equals b. So let's move over. We can divide both sides by 2 and eliminate those 2's. So we have the square root of 25 minus x squared equals x squared over the square root of 25 minus x squared. Multiplying both sides by the square root of 25 minus x squared yields 25 minus x squared equals x squared. So 25 equals 2x squared, or equivalently 2x squared equals 25. X squared equals 25 over 2. X equals, now x we have already established to be positive. So we don't need to worry about a positive and negative here. X equals 5 over the square root of 2, which equals, multiplying by the square root of 2 over the square root of 2, 5 times the square root of 2 over 2. So presumably, the area of the rectangle will be maximized when this is our value for x. Now, make sure that your answer makes sense, if nothing else. Remember, x has to be between 0 and 5. It cannot be greater than 5. All right? The square root of 2 over 2 is less than 1. So 5 times that is clearly less than 5. So we're okay there. If we want to get the actual dimensions of the rectangle, remember that's x. That's not the base. The base is 2x. So the base would actually be 5 times the square root of 2. Again, the base is 2x. Negative x to x. The height is the square root of 25 minus x squared. The height is the square root of 25 minus 25 over 2, which is the square root of 25 over 2, which is exactly where we were here. So h is actually equal to x. And if we wanted the actual area of the rectangle, then we would simply multiply the base times the height, which appears to be 25. Since 5 times the square root of 2 times 5 times the square root of 2 would be 25 times 2 is 50 divided by 2. I won't ask you to check to make sure that that's a maximum. A minimum would clearly be if x were 0. If you had no base, or if x were 5 and you had no height. See, those are the endpoints for x's domain, 0 and 5. And at either one of those endpoints, the area would be 0. And clearly, the area there is greater than 0, so we know it's a maximum from our work with absolute maximum and minimum. Okay, one more. Another inscribing problem, but this one is 3-dimensional. Just a note here, when we're in class, you can't press a button to shut me up. But if something is not clear to you here, stop the video, rewind if you have to, watch again. All right, our problem now says that we are trying to inscribe a right circular cylinder in a sphere with radius 10. Again, we want to draw a diagram. A sphere with radius 10, and forgive me if that doesn't look perfectly spherical. Drawing this diagram, there is one element that will make or break you, and that is, how do you draw that radius? You want to draw the radius. Remember, the radius of the sphere is 10. You want to draw it to a point where sphere and cylinder meet. All right, the problem we want now is what dimensions of the cylinder will maximize its volume. So that's what we're trying to maximize, the volume of the cylinder. The volume of the cylinder is pi r squared h. Do not confuse that with the volume of a cone, which would be 1/3 of that. The cylinder, pi r squared h. Now, drawing this radius in that manner allows us to complete a right triangle whose legs are very significant. This is the r, the radius of the cylinder. This, going to the center of the cylinder, is half the height of the cylinder. Remember, our constraint is often an equation that enables us to write one of these in terms of the other. Well, that's what we have here by virtue of the Pythagorean theorem. This squared plus this squared equals this squared. H squared over 4, that is h over 2 all squared, plus r squared equals 100. Now in this case, I am not going to solve for h or for r. I've got an r squared in my equation, my objective function. I can solve this just for r squared, and I will not have to worry about using radicals. R squared equals 100 minus h squared over 4. I can plug that in. Substitute that in for r squared. Pi times 100 minus h squared over 4 times h. Volume equals pi times 100h minus h cubed over 4. That's my volume in terms of just one independent variable. There is, as it were, the holy grail of these problems. Once you get to this point, again, the mathematics is just mechanical. Take the derivative, set the derivative equal to 0, solve for the critical number. And this one doesn't require a chain rule, doesn't require a product rule, it's a simple power rule. All right? Note, I am not multiplying through by pi. The pi would not change the critical number, so there's no point in complicating this portion. dV dH equals pi times 100 minus 3/4 h squared. So, let's move over again. 100 minus 3/4 h squared equals 0. That would make the entire derivative equal 0. So 3/4 h squared equals 100. H squared equals, multiplying through by 4/3, 400 over 3. H equals, again, this is the measurement, the height of a cylinder. I do not have to say plus or minus, this is clearly positive. A real world measurement. H equals 20 divided by the square root of 3, or if you prefer, 20 times the square root of 3 over 3. R squared equals 100 minus h squared over 4. All right? R squared equals 100 minus h squared over 4. If h squared is 400 over 3, h squared over 4 is 100 over 3. So R squared equals, 100 is 300 over 3, so R squared is 200 over 3. R equals, well, let's see. Since 100 is a perfect square and is a factor of 200, R equals 10 times the square root of 2 over the square root of 3, which equals 10 times the square root of 6 over 3. And there are the dimensions. Now, before I go ahead, let me just again stop and say, do those numbers make sense? Right? You always have to ask yourself that question. Note, the radius of the sphere is 10, which means that the diameter of the sphere is 20. The height must be less than 20. Well, again, the square root of 3 divided by 3 is less than 1, so 20 times that is less than 20. And the radius, of course, would have to be less than the radius of the sphere itself. It would have to be less than 10. And the square root of 6 is definitely less than 3, since the square root of 6 is a little less than 2.5. So 10 times the square root of 6 over 3 would be less than 10. So the answers make sense at the very least. And that's how we do applied optimization problems, constrained optimization. That's all.